I wanted to just show you an example of something I mentioned just before, namely the spectra from a diatomic molecule. So molecules are like little harmonic oscillators because the bonds here act like little springs. And in fact, H2, two hydrogen atoms, or two protons bound by an electron, or which share an electron, they vibrate back and forth. And in this system, it's constantly vibrating back and forth. Even in its ground state, it's vibrating back and forth. As we just said, there's an energy associated with the ground state. But if I send in a photon here, then this photon causes that bond to vibrate even faster, and I can absorb that energy. It's also then possible for the photon to be re-emitted when the molecule wants to kick back to its ground state. So what's interesting about this spectrum here is you notice, well, what's plotted here is the rate at which photons are absorbed into H2+ as you pass a photon beam through a gas. And it depends, of course, on the energy of the photon, and the rate of absorption goes up at various characteristic wavelengths or energies of the photon, and notice that those follow an extremely regular pattern. One can even use that information then to gain some information about the molecular bonds. Since the energies of those bonds go like 1/2 h bar omega naught, and that has the spring constant in it as well as the mass of the particles in the bond, you can also use this to gain some information about the mass of the thing in the bond. And in fact, what's interesting is that different isotopes actually show different frequencies for these kind of diatomic molecules. So, for example, hydrogen is H2, so two protons bound together. Deuterium, D2, is made of two deuterons. A deuteron is an isotope of hydrogen, which has a proton and neutron for each nucleus, and these are what's bound together. Notice that the reduced mass of these two things is literally a factor of 2 apart. We use a reduced mass, not M as in the formula I wrote there, so actually M should have been reduced mass. And that's because the harmonic oscillator is derived for a spring attached to a wall, and there's a single mass at it. But if they have literally two masses at the opposite ends of a spring, then what's there is the reduced mass, where the system behaves like a single particle with a reduced mass. So here the reduced mass is twice as large for D2 as it is for H2. And notice what happens to the frequencies here. So it's the same force constant, it's the same bond between those two things, and there's a shift in frequency. And it's not exactly a factor of 2 because, remember what happens, it's inside of the square root in the denominator, so I expect a 1 over square root of 2 type relationship between these two energies of the bonds. And you can do similar pattern recognition here if I have another diatomic molecule, HC versus CO. The only difference here is I have a C in both cases. I'm swapping a hydrogen with an oxygen. As a result, the reduced mass changes, and I see some change in the frequency. Or I go from CO to NO. I have an oxygen in both cases, but I'm switching a carbon to a nitrogen, and again, I expect to see some change in frequency. Here, there's a little bit of a complication because the bonds are a little bit different. But the pattern kind of continues. So one can either look at these kind of patterns and learn something about the different masses of the things, and in fact people search for different isotopes of molecules, organic molecules, using the spectroscopic data, using reduced mass. or they use this kind of data to derive directly what the force constant is.